So let's begin. You guys had a question about converting a binary number to decimal. Ashley, is that what you want to do? Or do you want to go from decimal to binary or binary to decimal? It's your call.
Decimal to binary.
Decimal to binary. Okay, so give me a decimal number.
3,000, no.
It works. 500?
143.
543. So we have 543 decimal. I'm just going to put a little 10 next to that so I know this is a decimal number. And what I want to do is I want to convert this into binary. In order for me to do this, and there's two ways of doing it, there's actually more than two ways. One way is the division method where you divide by 2 and you keep on going at it. That's a very long process to do. I prefer using what we call the base place formula. And that is, I'm going to just start over here on the far right with the ones column, then a 2, then a 4, then an 8, 16, 32, 64, 128, 256, and 512. Now I could keep on going. I can go with 1024 if I wanted to, but that's going to be way too much for what I need to do. So now that I have my places set up, and where am I getting these numbers? Well, you notice I'm always doubling as I'm going from right to left, and that's because I want to go into binary. And binary has how many symbols? 2, base 2. And so I'm basically saying 2 raised to 0 gives me 1. 2 raised to 1 gives me 2, right? And I'm just doubling as I go. We good about that? Now that I have this formula set up, I ask myself which one of the places comes the closest to 543 without going over it. And so then I put a 1 underneath the 512. And then I'm going to remove that 512 from the 543. So I get a 0 here, I get a 3 here, and a 1 there. Does that make sense? Then I ask myself once again, which one of these numbers comes close to 31 without going over it? 16 is the closest I can get. What do I do about the other values, the other places in which I don't have, that I skipped over, if you will? Zeros. They have nothing, so they get nothing. And then I subtract 16 from 31, and I'm going to get 15. And I ask myself the same question. Which one of these values comes close to 15 without going over it? 8. Put a 1 underneath that. Subtract the 8 from the 15. Or the 15 from, or the 8, yeah, whatever. Remove 8 from 15. And I'm left with 7. And then I ask myself which one of these values comes close to 7 without going over it. Folks, right when I saw 31, I was thinking, gee, that's all ones after the 32 place. If I were to add up 1, 2, 4, 8, and 16, I would get 31, correct? But that's because I've been doing it for this long, and I'm just going to have you guys manually go through this process. So I get a 3. What value comes up close to 3 without going over it? A 2. And then finally a 1, correct? So the number 543 is 1, 0, 0, 0, 0, 1, 1, 1, 1, 1 in binary. You guys want to do a couple more examples?
Can we do binary to decimal?
Binary to decimal? Sure. That works out. Let me erase this and let me switch my colors. All right, so I'm going to deal with this with blue. We're dealing with a binary number. And I'm just going to write some random binary digits out. Now I know in the examples I've been giving you guys are usually 8 bits, but they could be anything. The only reason why I've been dealing with 8 bits is because we've been taking the octets, we've been taking the IP address and breaking it up into octets, which means 8 bits. We good about that? All right. Well, I'm going to follow the same base place formula, but I'm just going to flip it. I have my binary digits right here, and above it I'm going to write my places. Starting on the far right, what's my place value? 1. What's the next value? Next value? And so you just keep on doubling as you go. So I have 1, 2, 4, 8, 16, 32, 64, 128. Then a 256, 512, 1024. What's the other one? 2048 and 4096. Help me out, is that right? Did I double those correctly? No, I do make mistakes when it comes to this. So verify that, because it will alter the number. And this is why I tend to keep it really simple and only at 8 bits, because you get the point. Nevertheless, after I establish my places, I'm going to multiply down. So I just take 4096, multiply it by 1, and I get a 4096. I take my 2048, multiply it by 1, and I get 2048. 1024 multiplied by 0 gives me 0. 512 times 1 is. 256 times 1 is. 0 times 128 is. 64 times 1 is. 32 times 1. 16 times 1. 8 times 0. 4 times 0. 2 times 0. And then 1 times 1. Then I add that across. And gee, that's quite a workout. If I was smart about it, I would have made the number half as small or half as long. Let's see, 4096 plus 2048. I have a 4 here with a carryover of a 1. I get a 6144, I think. Verify that, guys. Just take 4096 plus 2048. And then I take the 12, so I add 512 to this. And I'm going to get 6656. Please check my math. Right now I'm good? All right. Then I take the plus 256, and I'm going to get a 2 here, a 1 there, 9 there, a 6. I'm going to get 6,912. I'm going to take that 6,912, and I'm going to add 64 to it. And then I'm going to get 6,976. I'm going to add 32 to it. I'm going to get 7,008. I'm going to add 16 to that. And then I add a 1 to that, and I should end up with 7,025. Is that what you guys got? Mm-hmm. All right. More examples? Next example I give you will be a little bit smaller than that, okay? But the idea is just the base place formula. Once you know how to do it one way, the other way is easy. All right, so let's do by midnight tonight. You'll see where this is going to become really important as this week progresses, especially in tomorrow's lab. And tomorrow's lab will be creating 3 types of packet tracer files, one dealing with classful addressing, the next one dealing with classless, fixed width subnetting, and then the last one's going to be VLSM. Okay? So last time we met, we were talking about classful techniques. And I gave you guys an abridged version, a rather rushed version of a classful table. And I said we used this back in the day because we didn't have the processing power or the memory resources that we do today. And so when a router received a packet, the router would look at the first 4 high-order bits of what octet to make their decisions. So what octet were the routers using, folks, to determine the network address? What's that? The first octet. Very good. And we would look at the significant bits. We good about that? When I mean the significant bits, we're looking at the leftmost bits. So when it came to a class A, what must the first bit be for it to be considered a class A address? First bit needed to be a 0. I'm going to lock that bit down with a red 0. And then what could appear after those zeros could be anything. Typically, the range would go from all zeros. So we have 1, 2, 3, 4, 5, 6, 7, 8, to all ones. So we have 1, 2, 3, 4, 5, 6, 7, 8. This is the first octet. And what would B look like? What was the bits that looked for? Remember, we had up to 4 bits we had to look at to make sure that it was a class A, B, or C. We actually did D and E, but we're not going to discuss that. We're only going to be talking about unicast addressing. It would be a 1 followed by a 0. Now, we're using that 0 as like a buffer. It's more of like a pattern. If it starts off with a 0 right to begin with, it's going to be class A. But if it starts off with a 1, well, I can't rule out anything else, correct? I know if it starts with a 0, it's a class A. But if it starts with a 1, it could be a class B, a class C, a class D, or a class E. Does that make sense? So therefore, it's got to follow with another bit. So if it's a 1, 0, it's a class B. You good about that? After that, it's just going to be a bunch of zeros for its starting. Or, whoops. All ones. The important thing is that buffer space, okay, the red digits. Let's look at class C. What are we going to do with class C? 1, 1 followed by a 0, okay? So we're going to have a red 1, 2 red 1s followed by a 0. Okay, do you see how class B and class C both begin with a 1? So that means the computer will go to the next significant digit and say, oh, that's a 1. If I have a 1 followed by a 1, can the computer safely say that's a class C? Well, let's look at class D. Class D is going to be a 1 followed by a 1. Class E is going to be a 1 followed by a 1. Does that make sense? So we have to put a 0 afterwards. After that, I go back to all zeros for the start, and then all ones at the end. So you got to think the upper one is the beginning of the range, and the bottom number is the end of the range. We good about that? And it's all I'm going to explore when it comes to these classes, A, B, and C. Those are our unicast range. D was used for multicasting, and E was for experimental. D would have a 1, 1, 1 followed by a 0, and then E would have all ones. Everybody's kosher. Now, you and I tend to see numbers in a decimal format, which we call it the dotted decimal notation. So in the next column, I'm just going to write these numbers in decimal so we can better understand that. A class A is going to go from 0, and I'm going to put this in quotations, all the way up to 127. And I'm going to put 127 in quotations too. So the first octet in decimal for class A is going to go from 0 to 127. Why am I putting 0 in quotations?
Because it's decimal.
Actually, let's do the next one. Let me do class B. Class B is going to go from 128, which I'm not going to put in quotations. And it's going to go all the way up to 191, which I'm still not going to put in quotations. And those numbers are decimal. Tell me, if I was going to configure a router to have a default route, what would I put in there for the router? 0.0.0.0, correct? And what is the default route used for? When a router cannot find a better match in its routing table, it'll pass every packet out to its catch-all route, which is called the default route. So technically, if a address begins with a 0, it falls to the default route and not to a class A. We kosher about that? So that whole address block is actually lost to the default route. Likewise, what does 127 represent? And this is why I'm putting it in quotations. Because I would like to say that a default route belongs to Class A, but we actually removed it from Class A. So what about 127? In your reading at the very end, and I do apologize, but Chapter 6 is almost like 100 pages thick. I gave you guys 2 weeks, if not 3 weeks, to read this stuff. You want to read it. At the very end, they finally bring in some troubleshooting techniques, and they talk about the loop back technique. When you ping an address that begins with 127.0.0.1, you're performing a loopback ping. In fact, it could be anything that begins with 127. So the 127 is actually set aside to represent what we call local host addresses or looping addresses. And what they're used for is basically troubleshooting protocol stacks. Another technique that they're used for, and if anybody's big about Unix or Linux, you'll notice when you start configuring services and host files, there's a loop address, which we call like the local host of a 127.0.0.1. It makes it nice when a service running on a server is being requested by an application that's also running on the same server. Like for instance, your server has a web service running at the same time having DNS running. We good about that? So let's say somebody on the server opens up a web browser and they're looking to access the intranet's web service. Do you see what's going on here? You're on the server, you're using a web browser, which is a client-based software. We good about that? And you're going to access the company's intra website. So you type in, let's type in myCCC. That's something that we store here locally. We good about that? The DNS service is also running on that same server. Remember, in order to go out to a web page, you must resolve that domain name into an IP address, correct? And when you go to configure a computer, isn't one of those entries a DNS server? You have to supply it with an IP address, subnet mask, a gateway, plus a DNS address. Typically at home, you guys would supply the DNS as well as your gateway address to have the same number. We good about that? But in this case, I would just use my loopback address of 127.0.0.1 because I am also the DNS server as well as the web server, correct? And all that'll do is it'll go down to layer 3 and stop, and then pass it back up to layer 4, and it'll never bother my interface card. So it won't go out on my local area network generating network traffic. It's staying local. Does that make sense? It's a great technique to use for troubleshooting because the only thing you're testing is to make sure the protocol stack is properly installed on your operating system. Right, Marcus? That's the problem that you had with your computer?
Yeah.
You had to download the new drivers to have the protocol stack installed. So just by pinging the 127.0.0.1 starts a very first step in troubleshooting. It eliminates software issues when it comes to the operating system. Okay? It also makes it really efficient for servers to access services within themselves. Clear about that, guys? So technically, a Class A will go from 1 to 126. How many networks then can a Class A handle? So if we're doing out this chart, how many networks? So the number of networks, because this is going to be a growing question as the class moves on. If I'm saying my range is from 0 to 127, you guys would tell me that I can handle 128 total networks. We good about that? But I need to subtract away 2, correct? Because I can't use the zeros and I can't use the 127s. So that means I can go from 1 to 126, but that gives me a total of 126 networks. So far, so good? How many addresses per each network can we handle? So we're going to say total host addresses. Well, this begs the question. If I'm at a Class A, What I should probably be writing down on my table are the parts that make up my octet. Sorry, my IP address. So let me write in red just a little reminder that I screwed up. And that is, I need to know my parts. Class A tells me that the very first octet represents the network part. And then what about the other three? So I wrote N for network, dot H, dot H, dot H, correct? I have 3 H's. So therefore, I have 24 bits set aside for my host address. Safe to say that? 2 raised to 24 gives me a total of about 16.8 million addresses. Now, back in a classful environment, what we were dealing with was when we assigned one organization a Class A address, we gave them 16.8 million addresses. If they only had 2 computers on their network and they wanted a Class A address, they got all 16.8 million. Why was that? Because classful determination, or sorry, network determination was based off of boundaries. Class A said the very first octet represents the network address. The last 3 represent the host. Let's look at Class B. Class B has a range from 128 to 191. However, it can only handle, let's see, 1, 2, 3, 4, 5, 6 bits for networking. So how many total networks can Class B handle? I take 2 raised to 6. And what do I get? 65,535. 36, technically. Because I go from 0 to 65,535, correct? What about the parts that make up a Class B address? We have a network, dot host, dot host. So it's almost a 50-50 split. We good about that? And what about the number of hosts a Class B license can handle? Oh, folks, did I screw this up? I did. Thank you. It's 14 here. Where did I come with 14? My apologies. And let me modify this number. I told you I make mistakes when it comes to this stuff. OK, first of all, I couldn't do all 16s. The reason why I couldn't do all 16 is because these 2 are locked up. So I have 6 here, but I also have to add the 8 bits for the second octet, correct? So 8 plus 16, sorry, 8 plus 6 gives me 14. So somebody help me out. 2 raised to 14 is what? 16,384? That's how many networks a Class B could handle. What about the size of those networks? Well, we have 2 full octets that we can use, correct? So 2 raised to 16 is going to give me 65,536 addresses. That's where that number comes from. We clear about that? So you guys help me with Class C. What's the range going to be for Class C? Looks good. To what? 223. Yep. So you could just simply convert this number back into decimal and you're good. What about the number of networks a Class C can handle? Now remember, I have to subtract 3. How many octets in a Class C represent the network? Let's look at our pattern. We started with 1 octet for the Class A. Then we did the first and the second for a Class B. So Class C is going to be what? So that tells me I have 24 total bits. But I have to subtract 3 from there because these are locked down, correct? Can't change them. So I have 2 raised to 21, which gives me what, guys? Now last week I just rounded them up to the native bits of 24, 16, and 8. But today I'm actually being precise, so it makes, because I believe you guys can actually handle it now. So what's 2 raised to 21?
20971.
So about 2 million? Is that what we're saying? That works out. And what about host addresses? How many bits do I have for my host now?
To the 8.
To the 8, which gives me how many? Okay. Where do we use that information at? Last week we were using this board, and I had a diagram roughly drawn, and I said, okay, here I'm hooked up to a router, and this router is hooked up to another router, and this router has 2 networks branched off of it. And I think I said like something was like 60, 27, and let's just make this one 14. How many networks do we have now? 4, right? We have 3 local area networks plus this WAN right in here. How many hosts make up the WAN?
2.
Because we have a point-to-point connection, correct? All right. Now, naturally, if you're back in the 80s and you were designing this network and planning this out, you would look at that table, A, B, or C, and you would say, what would the best class be to represent each of these networks? And how would you optimize that? You would look at the class, find out the total number of host address each class can handle, and find one that would come closest to what you have. I knew there's always a smart guy. You're willing to waste 16.8 million addresses for this little network of only 14 hosts?
Yes.
Yes, you are?
Okay,
If I told you back in the 80s that would cost you guys about $500,000 a month, would you still want to waste it?
yes.
Who would organize this?
I kind of need that for
Yeah. What the hell are you doing here? All right, so obviously a Class C would work out. What are we going to set for a network address for this network here? If we're doing a Class C.
192.
It's got to begin with 192 at least, right? Could it do 193? Could we do 194? We can do any number from 192 all the way up to and including what? 223? So, sure, we'll do 192. What are you going to do for the next octet?
Yeah.
Sure, doesn't hurt anything. Why are we doing that?
So true.
First 3 octets represent the network part in a Class C. We good about that? So as long as these other networks do not share the very first 3 octets, yeah, exactly. So this last 0 means something to us. From now on, I want you guys to know that a network address is when the host part contains all binary zeros. We good about that? A network address is when the host part contains all binary zeros. When you're using a Class C license like we're doing right here, what octet represents the host part? The last one, the 4th octet. So how many binary zeros would be in the last octet for a network address for Class 0? Sorry, Class C. 8 zeros. You good? Because we have 8 bits to represent the host. I make a big point about this because we're going to switch this technique to classless. We're good about this? So what about this network right here, the WAN? What is the network address I'm going to use to identify this group of devices? I could do 192.0.1 followed by what? Because I want the network address. .0. Because the network address, by definition, is when you have all binary zeros in the host. Remember, a network address is just a group of hosts. We good about that? So this network address is going to represent this network right here. This one represents the 14 hosts for that network above. What about this? What are we going to do here? Oh, let's do the 60. That's sort of like clockwise. Let's do the 60. What are you guys going to do for this network address? And all we're doing is changing the third octet as we go, which is kosher because all we have to do is change any one of the network octets to get what we want to do. I could have made the first one 193, made this one 194, and then made the next one 195, and I'd still be following the rules. Good about that? Question is, why do I need to have uniquely identified network addresses? So I'm assuming you guys would make this one 3 for following the pattern.
I want to make it 4 actually.
You wanted to make it a 4? It works for me. But why do I have to uniquely identify each of these networks with their own network address? What happens if I decided to use the same network address for these two networks? And a packet comes in. What is the process going to be? What's the routing table going to look like for this router? This is Chapter 5 stuff. Chapter 5, Chapter 6, and the last chapter of this book, Chapter 11. And I guess I can include Chapter 10. So let's just say 5, 6, 10, and 11 are the most important chapters you can ever get from this course. Not only important if you want to pursue a network administration career, but for your own home, folks. This could be saving you guys $100 an hour to avoid a technician coming into your house. Chapter 5 is talking about how a router processes information. I said when this router first boots up, it's going to know about 3 networks. What are the 3 networks this router is going to know about? The 192.0.1.0, correct? But it should also know about this network right here, the 192.0.2.0. But there's a problem. What is the problem? I have another interface, another way out to that same network, but those 2 networks don't belong to each other. So when a packet comes in destined to 192.0.2.1, the router doesn't care about the host address because the only thing it looks at is the network address, and now it has a fork in the road. Do I go left or do I go right? I have a 50% chance of getting this right. Is host 1 on this network or is it on that network? Hence why you'd get an error if you tried doing this. And we need to keep them unique. We good about that? How does a router determine the destination network address when all they're given is a host address, like 192.168, 192.0.2.1? In this case, it looks at the first 4 bits of the first octet and says this is a class C. Look at 3 octets for the network address. We good about that? In this case, this is a classful addressing, and we are being extremely wasteful here. Because this network only needed 16 total host addresses. Why did I say 16 and not 14? And get used to this habit. Why am I adding 2 to 14 hosts? This is an address that I have to count for. And what other address must I count for a network? If a network address has all zeros in the host octet, what do you think a broadcast address will have in the host octet? All ones. And the broadcast address is the last address in an address block. What would the broadcast address be for this network? I'll start you off. It's got to be 192.0.0, right? Because the broadcast address and the network address, as well as usable host address, must belong to the same network. 255. How did you get that? Because you looked at the 4th octet, and you realized the 4th octet has 1, 2, 3, 4, 5, 6, 7, 8 bits, correct? And all 8 of those bits are filled in with 1s. So that means I took a 1 plus a 2 plus a 4 plus an 8 plus a 16 plus a 32 plus a 64 plus a 128. Folks, I would never add those up. You have time exams. Here are some techniques to save yourself some time. What is the next place? If you were to roll up, it would be 256, correct? So the next place would be 256, and right now that looks like that. If I were to add 1 to this number, these would all roll to a 0, and then this one would roll to a 1, correct? So 256 looks like a 1 followed by all zeros. What's 256 minus 1? 255, right? All ones. So if I see all ones, I'm just going to say to myself, and that is 8 ones, 255. Nice little shortcut. Likewise, if I had 7 ones, what would the decimal number be? 127, correct? Because it's the number right before 128. If I had 5 ones, what would it be? 4 ones. Guys getting the idea? This will come handy when you need to calculate broadcast addresses. I don't want to see on a sheet of paper 8 numbers being added together. 1, 2, 4, 8, 16, 32, 64, 128. You guys can do it. You'll get the right answer, but it's very timed. Your next exam is 55 minutes long, and you will have a 40-point question dealing with VLSM. And in that question, I'll be asking you guys to calculate the network address, the broadcast address, and usable ranges for, I think, 7 or 8 different networks. What's that? VLSM. So variable length subnetting mask. Okay? So now that we have this range, network address being the first, all zeros, binary zeros in the host part, broadcast being the last, all binary ones, I have to include that. In my logical diagram that I have, I said I need 14 hosts, but I need to add 2 to that because I need to include a network address and the broadcast address as part of the address block. We good about that? So how many addresses do I need for this network here if I have 2 hosts specified? Right? And then this one I would need 62. And this one over here I would need 29. The real burden becomes when this number becomes like 30 or 31, and you're not sure if you need to allocate 5 bits or 6 bits, which we'll get into now. That's Classful. The only times you really need to learn this is when we do routing protocols, which we won't cover in this course, but also when we start getting into, I don't know how I want to say this, our subnet problems. When you're given a class address and they ask you what subnet you're in, they need to know where the class boundary is and then find the difference between the host and the class boundaries. That's on Wednesday's class, all right? Very wasteful. I told you on last Friday, or last time we met, which was what, Wednesday? I said to you guys that we will be talking about 3 techniques. We'll start with the most inefficient technique of classful addressing. We're going to be working our way down to the most efficient. The next technique that we're going to be exploring is going to be classless. Classless is the technique that has made IPv4, sustainable, very popular, because it gets rid of this notion that a network address has to fall on a boundary. Did you see in these examples, class A, B, or C, the network address was whole octets? It was the first whole entire octet, or the first and second octet, or the first, second, and third. There was no splitting an octet in half. We good about that? Did you see throughout this whole process I never introduced the subnet mask? There was no need to. I taught you a simple rule. Look at the very first couple of bits in the very first octet, the high order bits. Once you have those bits, away you'd go, right? In classless, we actually need a subnet mask. Now I'm going to show you by using an example of how subnet masks are used through routers or through end devices to determine what the network address is. However, I need to also show you how backwards compliant classless addresses are with classful addresses by implementing default subnet masks. Have you guys noticed when you typed in an address in your computer, or even through Packet Tracer, that when you clicked on the subnet mask box, it automatically filled out certain numbers? You'll learn out why that is in a moment. Let's say I'm given an IP address of 192 168.168.20.73. If this is all that I'm given, heads up, because this is an exam question. If this is all I'm giving, if this is all that I am given, then you guys need to assume classful techniques, okay? Then if I ask the next question, what is the network address for this host, you would tell me what? If this is all that you're given.
192.168.20.0.
That's correct. So the network address, if all you're given is this particular IP address, you would tell me it's 192.168.20.0. But what if I give you this? A /27. This /27 is called a network prefix. Okay? And I love this prefix. I actually like it better than subnet masks. And after you guys get the concept of a network prefix down and subnet mask, that's all I'll be using throughout the semester. I won't be writing out 255.255.255.0. One, it's a mouthful. Two, it takes too much time. Okay? I'll just be writing a prefix down. The subnet mask and the network prefix are one and the same. We good about that? Their purpose is to inform the host, whether it's a router or the intermediate, or an end device, how to calculate the network address. Okay? The reason why I like the prefix, the network length prefix, is because that tells me that I have 27 ones to work with. So it tells me 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Do you see that? This is for the first octet. This is for the next octet. And I'm just drawing out my subnet mask. 1, 2, 3, 4, 5, 6, 7, 8. So now I have 24 plus what? 1, 2, 3. That gives me 27 ones. Do you notice the 25, 26, and 27th one ran over into the fourth octet? What do you think I'm going to put in after those 27 ones? 4, 5, 6, 7, 8. So I put in 5 zeros after my 27 ones. Why did I do that? How many bits make up an IP address? 8 times 4 is 32. A computer doesn't see it with dots. We see it because it allows us to break it up and make it a lot easier to group those bits together, right? All a computer sees is 32 zeros and ones. And here's the nice thing about some binary logic. It's either one or the other, correct? Either you're sitting or you're standing. The lights are either on or they're off, correct? An IP address only has two parts. Either the part's going to represent a network part or it's going to represent a host, but it can't represent both. You good about that? So what do you think ones would represent in the subnet mask? That the bit above it is contributing to the network part. We good about that? What do you think zeros would represent in the subnet mask? That the bit above it represents the host part. What I like to do is I like to draw a line. Unfortunately, you can't mix decimal with binary. In order for you guys to be able to calculate network addresses, you have to have both the IP address and the subnet mask in binary. We good about that? So I need to take my 192 and convert it into binary. That's a 1 in the 128, a 1 in the 64, and then all zeros. You need to get that comfortable with binary. It should take you a couple of seconds to convert a decimal number into binary. Watch the videos, do the assignments. There will be plenty of practice. Make sure you're going over them. I will ask from now on at the beginning of class if you guys need me to do some binary exercises. Take advantage of that time. Okay? Let's see, a 168. That's a 1 in the 128, a 0 in the 64, a 1 in the 32. That gives me 60. A 0 in the 16, a 1 in the 8, and then all zeros. Now in a moment I'm going to write it larger. 20. That's a 0 and a 128, a 0 and a 64, a 0 and a 32, a 1 and a 16, a 0 and the 8, a 1 and a 4, a 0 and a 2, and a 0 and a 1. 20 is just a 16 plus a 4, correct? So I just found where my 16 place was, put a 1 in there, found where my 4 was, and put a 1 in there. 73. 0, 1 in the 64, a 0 in the 32, a 0 in the 16, a 1 in the 8, a 0 in the 4, a 0 in the 2, and a 1 in the 1. I'm looking at 73 and I'm thinking I can get a 64, an 8, and a 1. 64 plus 8 is 72 plus 1 is 73. Good about that? So like I said, I'm going to write this out a little bit much larger for us to see that. But it's 1, 1, 0, 0, 0, 0. 2 more zeros. I'm going to put a dot here to help me know that that's in the first octet. Then I have what? A 1, 0, 1, 0, 1, then all zeros afterwards. 1, 2, 3, 4, 5, 6, 7, 8. Followed by a dot. And then we did 20, which is going to be 1, 0, 0, 0, 1, 0, 1, 0, 0. Is that right? 128, 64, 32, 16, 8, 4. And then I have my 73, which is going to be a 0, 1, 0, 0, 1, 0, 0, 1. 1, 2, 3, 4, 5, 6, 7, 8. This is why I like my network prefix. It tells me 27 ones. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8 gives me 24. 1, 2, 3. And then all zeros. Now I can draw my line. What do you think is to the left of that line? What portion of the IP address is to the left of that line? Got it. What do you think is to the right of that line? Wherever those zeros meet those ones, that is in this case the blue, the subnet mask, I have it divided up. Correct? A computer can't make logic out of that. They can't do what we can do visually and see if the whole number stream is like this and draw a line and say, okay, my network address is to the left, my host is to the right. What a computer will do to calculate the network address is it'll AND the top with the bottom. And that will produce the network address. You guys familiar with binary logic, digital logic, the AND operation? The only time you'll ever get a 1 is when both inputs are 1. Okay? I will look at it bit by bit as I walk my way down through this and AND the top with the bottom. I will AND my IP address with my subnet mask. So I have this for you guys. This is my subnet mask. And the red's my IP address. 1 and a 1 gives me what? 1 and a 1 gives me? A 0 and a 1 gives me. So anytime I have a 0, I get all zeros, correct? So I'm just going to fast forward this. Now, will I ask you guys to do this on the exam? No. I'd ask you to use your visual sense and divide the line and then calculate out. But am I going to show you how a router does it? Absolutely. So we're using binary adding. And I see a 1 here, a 0 here, a 1 there. That's what's nice. Am I not getting the same thing I'm getting back? 0 here, 0, 0, 1, 0, 1, 0, 0. So far, life is good. This is where things start to change now. I'm going to get this back. Because 0 and a 1 is a 0. A 1 and a 1 is a 1. A 0 and a 1 is a 0. But these are all zeros down here, correct? So what I'm going to put in here for this? All zeros. What was the definition of a network address? When the host part has all zeros in it, correct? Now let's convert this back into a decimal number so we can configure our routers properly. This is where we need to learn our places, correct? This is a 128. This is a 64. The rest are all zeros. What's 128 plus 64? $128, 32, 8. $128, 64, 32, 16, 4. Interesting. 64. Notice the network address is 192.168.20.64, not .0. Starting to see the difference between classless and classful. In classless, in Classful, I couldn't do this. I couldn't split an octet. I would have to draw the line at the end of a whole octet. And the furthest I could draw that line was right here, after the third octet. But in classless, I can say, let me go further. Now I can ask a whole bunch of questions with just this workup on my board. How many hosts can this network handle now? See, I borrowed 3 bits from my host. My host originally had 8 bits because I was dealing with a class. We good about that? But now if I borrow 3 bits, I only have a total of 8 bits for my host. 5. 8 minus 3 is 5. What's 2 raised to 5? 32. This network can handle a total of 32 host addresses. By the way, if I had to configure my computer with this new classless address, what would my subnet mask be? All ones, what would that be? So all ones is going to give me 255s. But no longer am I going to put a 0 at the end anymore, right? Why am I not putting a 0 at the end? Because I have these 3 right up there. This is a 128, a 64, and a 32. So I'd configure my computer now to be able to have a new subnet mask of 255.255.255.224. What do you think the default subnet mask would be for Class A? 255 divided by all, followed by all zeros, correct? What do you think about a Class B? 255.255 followed by .0.0. And what do you think Class C would be? 255.255.255.0. All right, tomorrow we'll be exploring both classful and classless in labs.